Right, so this is the exactly halfway. We are 10th class. So lecture 10, today we are going to discuss more on nanotechnology, or how to use nanoparticles to remediate contaminated groundwater, or at least the principle behind it. Announcement again, same thing. Last class, we homework 3 is due today, midnight. But if you are struggling, just ask. If you don't ask, I will not know whether you are actually doing it right or not. If you need extension because you have, whatever reason, because it's COVID time, I can't really feel for you. If you're just let ask for extension. Again, this is the last homework, so it doesn't really matter. But it's very important that you work on it, because uh, these 3 homeworks are part of the exams, midterms on February 16th. And project outline, we really need to have this one done by next week. The reason is, once you have the project outline, you'll start working on it. So the second half of the class will be mostly working together on those projects. And we'll also have a different concept we learn in the class, but it's really project is, there is no homework. That means I expect you to spend time on your project. Office hour every week, 2 to 3 p.m.s. Quiz. I also want to little bit talk about the quiz, because I know that last quiz the average was 7. It's not like a bad average. Every year students, some quiz, always one quiz is worse than other. That's why I kept it every best 3 or 4. But also I learned based on at least one student put a comment that some of the question, at least one question, he or she thought that the viscosity questions, that how viscosity change with temperatures, and then viscosity is also related to hydraulic conductivity. It was not emphasized enough, so it is very easy to miss for students. And I do agree with that, because if I put myself in your shoes, um, if it is not really clearly a lot of things is discussed, if it is, I expect that you should know from CE153 or some other way, it's always challenging for quiz. um, so what I need is, these kind of comments are helpful, so I keep in mind when I set question next class. And also for the quiz 3, on the next class we'll have a review quiz, or we'll just discuss these are the topics, this is the just overview, so that these are the questions you need to, or topics you need to think of. um, that way you have some kind of like midterm review, you have a quiz review. We'll just summarize what we learned. That 10 minutes is probably going to help you a little bit more, just in case some of the questions are relatively less discussed during the lectures. But in my own experience, the quiz 2 was the hardest quiz, always in every year. Quiz 3 and 4 are very similar to quiz 1. Most students do well in quiz 3 and 4. Okay, so and also the intention is quiz 3 is also very much related to different projects. You got to think a little more creatively, so that also helps. Having that um, challenge is also helpful for us to think. But I would not worry too much on the grades, because it's just one quiz. You can have a bad quiz, and on the second, this class is designed such a way that your project is kind of 50%, and most students, all teams do well, because if you spend 5 weeks working on it with me, so very less chance that you do poorly on projects. Very, very. I have never seen that any project was really bad. But you have to start working early. That's how it goes, and you are working. And midterms, again, this midterms is very much you have just few homework 2 and 3. One is very much simple questions. So as long as you are comfortable doing the homework, you should be able to do all the questions on midterms. And there will be short questions on midterms. Those are related to at least quiz or some small questions. But typically it should not take more than 2 hours. And I will try to make sure that it's not taking that long. Like we had CE153, it took longer. That's not my intention. And again, it's open book. You should be able to submit 24 within 24 hours after release. But once you open it, you have 3 hours. Project outline we'll discuss at the end if you have any questions, but you got to meet with me if you have not met as a group, because it does help. What I It's not required that you have written something in the outline to discuss with me. It's always just meeting and we can brainstorm if you have struggle in any way. And I provide very specific strategy. This is something I know over years it works. What I do is I break it down to small tasks for each students, and each students then are very know exactly what they have to do, and they spend 1 to 2 hour maximum to get it done, and then collectively you have some materials. So the few things that I need when we discuss is your curiosity, because what I do is I break each project into a couple of questions, or even each paragraph into few questions, and based on what is important or relevant for your project. And then I give you some tips how to search answers for them. And then you just write a few lines here and there. Look for references using Google Scholar based on that questions, and you just give some tips for yourself in future to start writing those paragraphs. So it's not that difficult. That's how we also write a manuscript, journal articles. It's the same strategy I'm helping you write or develop a very early stage. So meet with me if you have not done it so far as a team. So send me an email, and also have your own Zoom link or Zoom ID. That way I can join in and then you can continue discussion with your teammates. Okay, so that's all for the announcement. Any question? I don't see. Let me see any chat window. Um, I don't see any questions so far. Okay, so learning objective. We are going to learn about nanotechnology, at least how you can use nanoparticles to remediate contaminated groundwater. The principle behind it is not like we are designing anything. And so that way, if you have a projects where you can employ this technology, you can always work on it. So again, the question is, few things you should know at the end of this class is different types of nanoparticles, because nanoparticle is basically anything less than in the nano range. But it has different properties, it has different based on materials, so you learn all that. And then you'll think of why the small size makes it efficient. What changed when the size changed to nanoparticles? What's the difference between a nano gold versus a big gold? Because we can wear gold, nothing will happen. But if you make it nano size gold particles, it has a different properties, and why it develops, and what's the reason behind it. And then what's the principle of remediation of using nanoparticles? What are the different stuffs that you have to think of when you are using nanoparticles? What's the challenge? What could make the nanomaterials less effective in the environment? All that you will learn, so that when you have a project, you can apply those concepts. Um, so now the very first thing is nano nano-remediation. First thing to think of is nanoparticles. Nanoparticle is, as you see over here, anything of the size in the range of nano range. So 1 nanometers is 10 to the minus 9 meters. And what does that mean? If you see, water molecule is 1 Armstrong. So that's 1/10 of a nanoparticles. That's the size of water molecule, one water molecules that you see over here. If you go to the other end extreme, as over you see here, um, I mean, if you think of bacteria, those are 1 micron size. Not two. This will be around 2 micrometers. If you are thinking of coronavirus, that's like 1/10 of a one less than 1/10 of a bacterial size, so 100 nanometers or lower. So that's the virus. Okay. If you go even lower, 10 nanometers, that's over. This is the range 1 meter. This is 10 nanometers. This is 100 nanometers. And if you see this, when you say nanoparticles, we typically consider nanoparticle less than 50 nanometers or around those range. Even though 100 nanometer is a nanometer, it's really that the properties start changing once it become more than 50. It's smaller than 50 micron or 20 to 30 micron or smaller, the effectiveness is higher. As it become bigger, it's become less and less effective. So when you think of nano remediation, we are looking for particles size between 1 nanometers to roughly 30 nanometers size range, effective for remediations. Think of this way: it has to be around the size of virus or smaller than virus, not higher than that. Okay. So now, as you see, nano is just the definition of size, anything within that size. But why it is, what changes as you make it smaller and smaller? Why it is so effective? Well, the first thing it changes is reactivity. It turns out the material property, how they react, is very different. The size is small. I was talking about gold. We wear gold, nothing will happen to us. Even you have a silver particles, nothing will happen to you. But if you make it smaller and smaller at very small scale, that's where in our cells and all the cells, organisms, the size of the pores, everything are within that range. That means now you are talking about a size where the interaction will be much higher. It can penetrate into the skin. It can go other places. So that's why nanoparticles are effective reagent. In fact, if you think of sunscreen, it has a zinc oxide or titanium oxide. Titanium oxide is initially used. Later, it was found that it can cause other disease, for instance, cancer, skin cancer, because if you have too much titanium oxide, it can create the whole skin and UV radiations. Not only it block UV radiation, it create radicals, and that's why it is replaced with zinc oxide. So next time, if you look for sunscreen, look for whether it's a titanium oxide or zinc oxide. Usually, the one zinc oxide, which is expensive, titanium oxides are still, as long as you have a small quantity, should be fine. But there is always a change in um, product now, mostly zinc oxide base. So the point here is that if you make it smaller and smaller, it start becoming more reactive. And this is what I write here, less than 30 nanometer, that's where the reactivity starts showing prominent enough for any applications. And so just a concept, if you think of as just a soccer ball right on the top, that's like a big particle. If you squeeze and smaller, uh, 0.2 billion nanometers um, is the size of ball. That means now you can fit that many, almost a billion nanoparticles across it. Um, Okay, so basically it means it's small. So now question is why the reactivity is high. This is just the principle it shows. It's all about surface area because the reaction happen at the surface. So if you have more surface area, it becomes more reactive, and it's just how it works. So if you see over here this cubicle, just example, if you count how many side it has, three sides, and each side has how many small cube. For instance, here one side has 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3 square. So and then you know that it has 6 sides. So multiply 6. That's become 54 space. Okay, and if you divide on the volume is obviously 3 over here. So I multiply that, it becomes 27. So surface to volume ratio is 2 in this case. If you make it 4, it does the same thing, it becomes 3. If you make it smaller and smaller, it just basically means it has 6 times more surface area per unit volume as you decrease to smaller and smaller size. If you decrease the size to 1/3, the surface to volume increases by 6 times. So the reason because of that you have more reactions. So let's say we write a generic formula why sphere is more effective. or the nanoparticles. Let's say the nanoparticles are spherical size, which is most of the case in the world. So if you think of sphere, the volume of nanoparticle or the sphere is 4 by 3 pi r cube. That's the volume of a sphere. If you think of area, 4 pi r square. Okay, so if you divide, if you see how much reaction per unit materials, because that's all it matters, how much you're adding in a system. So this will be 4 pi r square. Okay, so it's basically 0.33. Um, okay, so if you plot this one, so this is basically area per volume. Volume is related to materials, how much materials you have. Area is the reaction. So another equivalence is reactions per how much materials as related to volume, how much reaction, because it happens only on the surface. You can talk relatively area per volume. So that means, so normalized reactions that's per unit material, how much reaction you can achieve per unit materials. Um, oh, you're right. I'm making mistakes. There should be 3 because it's 1/3. So it should be 3 by R. So if you plot this one with the size as, let's say, R equal to 1, it will be 3, right? So let's say this is R equal to 1, it's going to be 3. This is 1, this is 3. R equal to 1, this is 3. Let's say that's how it goes. R equal to 2, it will be 3 by 2, 1.5. So this will be 1 up. So if you go down, it will go like this. If you make it, let's say, R equal to 0.5, this will be 6. So, so this is how it will, okay. So what it means? It means that as you increase the size, the reaction is exponentially, not exponential, it's obviously it's not there is no exponential term, but it does decrease 1/r. So that's the reason. As you as you decrease the size to 30 nanometer or smaller, you will realize this number is so high that the reaction itself is spontaneously created because of its small size, irrespective of what material it is. So every nanoparticle has high reactivity because of the size. And so anytime you are looking for remediations or using nanotechnology, you have to maintain that size. So most of the challenge is always related to size. Can it be nanoparticles for in the system? Because you will realize in some point in the slides that they will not stay as nanoparticles. There will be a change, and we'll learn that. So before that, a little bit background. When I say nanoparticles, there are many types of nanomaterials because it can made of metals, as you see over here. It can made of silver, gold, palladium. That's a catalyst, and copper. Copper is a antimicrobial agent. So you can see that you can use the metal particles as very nanoparticles. And because metal particles are, once you make it very small, if reactivity increases, it can spontaneously start reacting with oxygen, atmospheric oxygen or water. So that's why you cannot have nanoparticles metals as it is in the environment because very reactive. So normally when I say silver or copper, everything, I'm talking about iron oxide or metal oxide. So that's why you see over here is the metal oxide nanoparticle, zinc oxide, because zinc itself is not stable. At the very small scale, it will start reacting with atmospheric oxygen or water. So what you see over here is actually the oxide form of that metals. So you see in the sunscreen, zinc oxide is used. That's the zinc oxide. And then also you have multiple types of nanoparticles where you have a kind of coordination bond like carbon nanotubes. So anyway, so metal could be one form. Then organic, it's related to naturally we have this mixture, these hybrid type of surfactants, biomolecules that could arrange such a way that it will produce this kind of products. And then you have carbon nanomaterials like graphene, fluorines, CNT, carbon nanotubes. Carbon dot means much smaller, just a small portion of it. Um, and uh, and then all these other things you can see, graphene is something recently a lot of people use, and so these are all carbon. And to increase the reactivity, a lot of times you can replace with a metals. If you put a metal here, it can act as a catalyst, not just carbon because there is imbalance there, so there will be much more reactivity. So these are the different things people, in last 10-15 years people start modifying these to create product that serve different functions. Nanoparticles can be also used as a sensor in our human body. They inject nanoparticles so that they can see where they go, just like a treasure, fluorescent nanoparticles, so they can put a tag on it. So there are humongous type of applications. In fact, if you any materials we are now wearing or using, it has nanoparticles for some functions. For instance, if you think, let's say we have your shoes or your socks, all those things, or any kind of let's say underarm products that if you have too much sweat, it can stink. So that's the reason they use nanoparticles to kill any kind of germ. So that's why in the socks or shoes you have also nano coatings to kill any germ in your feet. So it has really, really a lot of applications. But nanoparticle can have also unintended consequence. It can be toxic, it can be reactive. That's how we also see that most of the sunscreen initially was made up of titanium oxide. Slowly, slowly, they're phasing out and putting as zinc oxide because it has less reaction with the skin. And
Professor, I have a question about
yeah,
sunscreen.
yeah.
So sunscreen in like that are advertised are either like chemical or mineral. What's the difference? Do you know?
So I think I have to check what's the label, but most of the sunscreen is made up of minerals, like, that's the zinc oxide and titanium oxide. They're naturally present. So it's really not some chemicals, it can be chemical because metal, but they are naturally also present. But it's not like they take mineral from the environments and grind it, and that's how they create sunscreen. That's not true. They have some composition might be like that, some clay, but mostly it's titanium or zinc oxide based nano, method. But that's why I say, anytime you, let's say, go to next product, just take a screenshot or pictures of them and see what compositions they are made of. There are a lot of different stuffs there. There are some organic base. They are looking for this zinc oxide. They are tagged into organic molecules, so it is not really, you know, um, cannot penetrate into the skin. They stay on the surface, so it'll react with the UV light because that's all they do. UV lights, um, titanium oxide, they can absorb UV light and excite it, and they go to ground state without really causing any damage. So they have this. The absorption is almost similar to UV light's range. Any other particles, they're the band gap or the way that absorption work, atomic absorption, the electron will jump and then will come back to the state. That difference has to be matching with the UV light. And it turned out titanium oxide has a wavelength that's related to UV light. So that's how they absorb without really causing damage. Um, but zinc oxide can do. So why not any other? Because of that band gap. The electronic cell, when they jump, they don't really have the same energy. So, it's an interesting concept. If you see nanoparticles in sunscreen, you'll find lots of articles. You'll learn from all this. The concepts are very similar. Okay, um, so what we learned that nanoparticles could be of different materials. Or nanoparticles could be also different size or shape. As you see over here, that could be 2D, two-dimensional. Graphene is a 2D. It's a sheet. Then you can think of nanowire, and that's like a shape, wire shape. And then you have also dot or spherical, and there are multiple different kind. So here we are not talking about materials. We are talking about shape. And why it is important? Because shape can also influence how they behave in the environment, whether they aggregate or not. For instance, nanowires, those could be used to connect between electricity between materials. So it helps to connect with different branch. So there are some applications where you need that, particularly creating conducting surface. So that's where you add nanowire. And spherical, anytime you want to move stuff, let's say use as a tracer or reactions, they can be more effective because it's everywhere symmetry doesn't matter. Any side should be same. Um, and but you will also learn in a couple of slides that nanoparticles do not stay as nanoparticles. They will aggregate because they will interact with each other. So this is just to show that nanoparticle has many applications. If you see cosmetic, skin, any kind of skin products has um, nanoparticles. Then you can see tennis racket that makes it strong, the recoil, so that gives the nano coating, so that makes it helpful. Solar cell, it increases the UV absorption because as you see, the light has to be absorbed. So they use nanoparticles on solar cell. In fact, there are many products. Almost everything has a nanoparticles applications. Semiconductor efficiency, heat, how the heat dissipate, all that is all related to nanotechnology. And then if you come back to the biological process, nanomedicines, where they apply nanoparticles, which can deliver the drugs at specific locations. They can encapsulate in the drugs inside the nano coatings. So all that is there. Then also imaging, as I said, it can use as a tracer. It can be tagged with a fluorescent color or dye, and nanoparticles moves. Because if you think of our cell, the blood cell, the size is nanoparticles. In fact, a little bigger than nanoparticles. So those are the blood cells, the blood hemoglobin, that blood cell that moves. You can put those nanoparticles there, so it can go in our body and then get to the direct point. And it's very important applications because imagine if you have a cancer cell, somebody has a cancer in her organ, and that particular locations has different compositions. If we know how to distinguish that, we can use nanoparticles that will only react if there is a certain condition changes. So that means if you take the medicines, it's not going to attack your regular cell. It's only going to activate if the let me come back. It's a lot of noise. Okay. Um, So now you see that it has its own applications. And I was talking about cancer cell because cancer cell may have a different composition. The pH could be different. The chemistry around it could be different. And you can use nanoparticles that could release that drugs or only when that condition changes to that locations. So that's why it can be very targeted. It can only target to the location that is affected as opposed to the entire body. Um, so then I talk about antibacterial agents where you can add nanoparticles to your socks and that could actually make it your feet will have less germ. And then water treatment. This is what we are going to discuss today. You can use nanoparticles for remediations. And this is one application that almost everywhere people talk about is you can apply a tablet. If you're going for you can apply a tablet in a water and that will kill a lot of pathogens and the germs, and then you can filter it and drink it. And so So that's the tablet that they talk about. And then you see on the top here, there is a portable filter. So basically it's a clay pot, and the clay was coated with nanoparticles, silver nanoparticles. So the idea here is that any bacteria, if you have a bacteria here and you have a surface with silver, okay, when I write zero, that means it's a silver metals, doesn't have ions. And so they release silver ion, and the silver ion can penetrate into the cell wall, and it's toxic. So it bind with the cell wall, it will destroy it, and then also if it get inside, it will also damage the cell. So it's all about silver ion, so that would break it. So the idea here is that if you put silver nanoparticles, it will dissolve easily, at least in the phase. If you put a large silver, let's say wear a silver, it doesn't change anything because so big that the dissolutions of silver is very, very low or nothing. So if you even if you wear a silver ornament, it's not going to change anything. If only when you make the size smaller, then it will start showing that effectiveness. So it just so that silver can also create reactive oxygen species, a different way they can break it. So silver is the reason how we can create a lot of different treatments. All right, so there is a quiz now, just to um, what is more toxic? Is this silver zero? That means it's not. I didn't talk anything about size here. Obviously, you can infer which one is smallest because ions will be always smallest. But it's these two are particles. This is ions. Okay. So which one is toxic based on what you learned just now? You have a 10-second more second to think about. We'll discuss that. Okay, so most of you, yes, what we discuss now, silver ions are um, is the reason why bacteria die. Okay, so it's not the particles. That's why otherwise you will have a toxicity. But as you decrease particles, only when it becomes nanoparticles, then you can release more enough of the silver ions. Okay, so the answer is silver particles. And if you do as a remediations, there are other particles like iron, zerovalent ions, and the size would be, let's say this is zerovalent iron, and the size would be, let's say, 20 nanometers, 10 to 20 nanometers. That's what we inject. And iron is naturally present in Earth. In fact, I think it's the second or third most abundant elements on Earth. So that's why you see all the irons every place. You have irons. Um, and irons, that's why now if it is natural, so that means if you apply this one, it is not going to change much. So that's why iron is a very, very good remediation agents, iron nanoparticles. So when you had zero valent iron, it is same as metal iron. Okay, so there is no difference. All it's saying is this is not dissolved iron. It's not iron 2. It is not iron 2 plus, or it's not iron 3 plus. Or that means it's only iron. 0 means zero valent iron. So that shape could build up, So that means you can make it smaller, smaller. Uh, you can go for as small as this process. Okay. Um, so as you said, every iron or any nanoparticles will react with what is out there. So when you're injecting water, it will react with water or oxygen. So that's why it will never stay as iron particles. It will become iron oxide. So even though it's iron, it will have a coating. Okay, so this is called FeOH2, or based on how it is done, Fe2O3. This could be any kind of, it could be any of these minerals. It's basically corrosion. Corrosion will happen instantly. The moment you add nanoparticles, atmosphere, even just leave it outside, within 30 seconds or 1 minute, it will start corrode. Um, so that's why all these nanoparticles, when you think of, they are actually iron oxide. Zero valent, it will go back, but it's not stay as zero valent. But let's say it will continue to dissolve. So again, application of nanotechnologies, you apply this one in a pump, you spray it, you hope that these nanoparticles will go to the locations and then will have that reactions. Reaction, there are many types of reaction. It could oxidize, it could reduce. That's the idea of iron particles. Iron is very efficient at many different ways. It can release electrons, because when iron goes to iron 2 plus, it it release two electron. That means it can induce reductions in the chemical reactions. It can also oxidize if the pH is high enough, because it will react with oxygen and produce another radicals. So these are different way it says, how we can remove um, um, contaminants using iron nanoparticles. The very thing at the inside, this is pure iron. That's what it says, zero iron cone. If you think of outside, that become corroded iron. So that coating is iron oxide, if iron hydroxide or iron OH or whatever the other things. And then it could have reductions, because the iron when dissolved, the electrons is released, and that electrons is absorbed by other contaminants. So these are different shape, and based on what type of mineral it form, there are different type of iron oxide, iron minerals. It can have different reactions. So again, anytime you think of this kind of technology, you have to think of what type of nanoparticles it is, and what form it is when you are injecting, and what it can become at the site. So again, I just show you the it can facilitate the reduction process, because it gives electrons. These electrons can reduce other chemicals. Okay. And there is other form of things. It can also produce hydrogen peroxide, or this is, I'll just say, radical formations. So it will produce it, because always they have oxygen present in water, and then it's react with oxygen to produce hydrogen peroxide, and then it will also react with that peroxide to produce hydroxyl radicals. This radical is called hydroxyl radical, and it's extremely reactive. In fact, that's one of the reason iron hydrox the nanoparticles are used for reduction of any kind of chemicals or oxidation or reductions. So it's really not nanoparticle, it's actually the OH is what's doing it, and the nanoparticle is helping creating those. The third one is, obviously it can stick with the iron particles. Once it grow, become corrode and aggregate, it will form big particles, and that's where it can start absorbing bacteria, other stuff. It can also absorb as small particles too. So these are the three methods. Number one, reductions. Number two, oxidation using hydroxyl radical. Number three, adsorption. These are the three ways you can remove contaminants. All right, so now if I ask you a quiz now, based on how the question is written, let's see how many, what do you think of this particular question? Does the reduction of iron depends on pH? This one, if it depends on pH, yes or no? It's not reduction of iron, it's actually um, oxidation of iron. So I'll not write this one, because Fe0 minus 2 electrons, it become Fe2 plus. Okay. So it's basically the zero valent iron is being oxidized. Okay, so I'm going to close the poll. The reason I'm doing this one is just to give a thought process. If you see over here, the answer is no if you see this equation directly. But think of what will happen. This is not the end of reactions. I wrote this one Fe. So if you are writing just based on this reaction, that answer is correct. But in practice, it's not true. The reason is iron 2 is not stable. Okay, it's going to react with water. Water means it has H plus and OH minus. So when it reacts with 2OH, OH minus, it will start precipitating. Okay, so that means it will start removing some of the iron or start precipitating FeOH, and FeOH will it will lose the water molecules. If you age longer and longer, it will create all these other types of minerals it will form by aging. Okay, so that's the whole process. The moment you add iron nanoparticles, it will go through all these transformations. The first one is instantaneous. The second, precipitation, is also occur very quickly. The third step, this is the first, second, third. So if you collect sample after like 1 day, you'll find these kind of materials. Okay, you'll not find that iron, zero valent iron anymore. So if you see the second step, it depends on pH. If the pH is high, you have more OH, you will not have this iron. Iron 2 will not stable. It will become precipitate. So if you think of what's really, the entire process, it does depends on pH. But if you're just looking for just the oxidation of iron, it does not depends because that itself doesn't have a pH. So in the oxidation, if you see the second question, that's where you have the pH. Okay. So that's why I asked the question here. Does the oxidation of iron by oxygen, which is this equations, increases with pH? Yes or no? So let me relearn this question if I have the squeeze, this one. Increases or decreases with pH. What I'm asking is if the pH increases, if this reaction will go forward or not. Because if it go forward, then it will increase. Okay, so I'll close in 6 seconds. Okay, so you see the answer. Let's see what's the right answers. As you see over here, if you increase the pH, if the pH increases, what does that mean even? It doesn't mean that H plus increases. pH increases means H plus actually decrease because pH is minus log H plus ion. That means acidic pH, which is the low pH, you have more H plus ion. It's a negative sign here. So if the pH increases, H plus would decrease, OH would increase. Okay. So that means if your H plus is increasing, you are adding more of this. That means this reaction, more reactant is going on. So it's moving in these directions. So your reaction will increase or become more efficient because you have more reactant side. So that's why that means it's going to increase that forward direction, which is oxidation of iron. So that answer is true. Okay, so now I wanted to just say that this is the how it works. In many of your, if you see these articles over here, you have iron oxide. It can react with, this is one example, TCE, which is chlorine, and so that chlorine is removed by iron because that gives that electrons, and then the chlorine become chlorine gas. It can reduce hydrogen. It can do all these other things. This just shows that these are the different processes that could happen. If you take a picture in a electron microscope, you will see the nanoparticles like this, and you will also see this range. These range are basically iron oxide, and this is zero iron. So you will see this is the big particles, and the center is iron core. This is the zero valent iron. This is the iron, um, the corroded products, oxygen. So that's why it expand. So when you apply that in groundwater, even you are applying very nanoscale, it is expanding. So that means it's also changing with time. This iron is becoming iron hydroxide. So and so that's why you have to also think of this expand. And so anytime you are applying zero valent irons to remove, let's say, stormwater treatment system, even if not nanoparticles, if you apply that, the volume is going to expand. That's why you never apply very high amount of iron as a filter in soil. The reason is going to become like a cement. It will expand. Corrode means it's going to create like a very um, um, cement-like structure because it's basically expand and there will be no more pores. It's like a solid cake. So this is corrosions, expansion of volume. That means it will decrease mobility because it becomes small, bigger and bigger. It's become heavier because now oxygen is being added to the system. So if it become heavier, it will settle. So it will not move faster. And if you have lots of big particles, and then it will start clog the pores. That means if your hydraulic conductivity will decrease. So you got to think of all that aspect. Once you apply nanoparticles, how much you should apply, how much pore size, all that. This is just example to show you. If you look at this particular articles, science published there, it shows that how they can apply nanoparticles to remove arsenic. Arsenic is one of the pollutants in Bangladesh, in that Southeast Asia. Bangladesh, Vietnam, all these places have a high concentration of arsenic naturally present in their aquifer. So if you pump water from groundwater, then you are exposing this oxygen from the top surface, and that release that arsenic. So that means arsenic 3 is highly mobilized when you oxidize oxidations of arsenic. Oh, I'm sorry. Highly oxidized is arsenic 5 because 5 plus. So this is highly mobile. Okay. So the way to decrease the mobility is to reduce it. So that's the way they use this iron nanoparticles to give that electrons, and so that way become arsenic 3. It will stay stable and also it will react. And what's the interesting picture here is that if you have a different size, if you apply the same materials but different size, the reaction is more efficient. And that's because, as you see, as the smaller and smaller particles, it has more surface area, reactivity. It just so that it has more adsorption. This is the concentration in groundwater. This is in water. This is in nanoparticles. It just shows that more adsorption will occur. Um, so we take a break for 10 minutes, 4:54 now. We'll be back at 5:05. Then we'll start discussing about applying nanoparticles for your projects and what kind of challenge it might have. So if you have any other question, you can put on chat window. We'll discuss that after we are back. Okay, so see you at 5:05. So 5:05. Resume. Okay, so what we learned so far is nanoparticles, all that background. Again, there is a nano, I think there is a class just on nanotechnology. So you will have entire class dedicated to this concept. So what I'm going to discuss now is when this is applied and when this is efficient, when it is not. So if you think of a concept of nanoparticles, nanotechnology, you have three things you have to come think of. First is material itself. Okay, is it nano size? What's the concentrations? Okay, how big it is? Concentrations. It's not right. So that next time somebody see what concentrations. Okay, and then what phase or what kind of materials. Okay, so these things you can determine pre-hand what kind of materials to buy, because these are things is related to your particular contaminations. So you know these nanoparticles are efficient, so you'll buy the materials. Concentrations and size, these are something smaller is better, but if you're too small, obviously they are going to react, aggregate faster. So that's one thing. And why I say why is it nano size? Well, we call it nanotechnology. It has to be nano size, but that's not true. If you create a nanoparticles, it doesn't stay as nanoparticles in long term. The size is going to change. So nano size is going to aggregate. So that means if you have a smaller particle here, they are going to aggregate and become like bigger. And once it becomes size grow, it becomes like micron particles. So that means it's no longer nanoparticles. And so that means not only its reactivity decreases, you cannot even inject them, because as your size increases, it's also difficult to inject. But it turns out, if you see the transport of particulates, I'll just write it here. So how efficiently you can deliver it. So that's number one. Then second stage, this is number one. Number two is delivery. Delivery means it's going to inject it. So when you inject it, it should stay as nanoparticles and it should be able to move. Because if you start reacting with all the soils and everything, it's not, you're going to lose all these nanoparticles very quickly. So it has to have a stable state so that it can be delivered. It should not be aggregated. So this transport is something is much more important. And so anytime when you think of nanoparticles efficiency, the part one or the material states and all that you can control. It's the delivery that makes the design fail. Because if it's not going to deliver at the location you want, no matter what you inject, it doesn't really matter. So that delivery fails because of the size, because of the reaction once it's released. And that reaction, number one is aggregations, another is also reaction to the surrounding. So there are ways to make it more efficient by adding some kind of coatings that doesn't makes them aggregate. We'll discuss that, like organic coating. So a lot of times they are always mixed with surfactants so that it can make it stable, so they can move along with that, or organic coatings. Um, so the react the if you see the size here, at the when the nanoparticle size are very small, it's very reactive. So the transport is not efficient because they are going to react with soil so efficiently. And so that means as you increase the size, the transport, the reaction will decrease. Okay, or the mobility. I'm just writing as a mobility wise. Okay, but as you go higher, the mobility also. So so let's say this is a retention of nanoparticles in soil. So the at some range, this is more less retention. That means more transportation, and that's around 1 micron. It's because how colloid works. And let's see what's the reason behind it. If become too small, if they're so reactive, they're going to interact because nanoparticles are very reactive, so they interact. As you become higher and higher, this is just for any particles. It's not nanoparticles anymore because they are aggregates, so their size is changing. As you become bigger and bigger, they can settle down by gravity. So as you go bigger, higher here, this is gravity is going to dominate. As you become smaller, just the interparticle attractions. Okay, so interparticle force will be higher. That's why it is attracted towards soil, so it's not going to be stable. They are going to aggregate so fast. So lot of times when you deliver stuff, it's become already big. So that's why there is a reason you don't want to go to one micrometer. So you want to stay in the smaller. They stabilize by adding in the delivery system. They add a stabilizer, which is basically a organic molecules. What it does, it attracts on the surface of nanoparticles, and then that prevent the interaction between nanoparticles. That's the whole reason. So anytime you see in the application, they always mix with something else. So this is just example, just to show it require just example successful success depends on high reactivity, so it becomes smaller. It requires a long lifetime. That means it will stay there for a long time now without becoming corroded or not corroded, changing the properties. And it should be mobilized. That means you can inject efficiently at different locations. So the way they work is you create a well near the contaminated zone. So like here, so instead of injecting from surface, assuming this somehow is going to find, which is never going to happen, you're going to really look for that locations, and then that's where you are going to release it, so that it's so that means the assessment is very important. Where the contaminated are is going to make a big difference in terms of efficiency of this method. Because if your diagnosis is like, okay, this is the location you thought, that's not where the contaminants are. If you inject there, that's where the nanoparticles will be. They are not going to release into different locations. Then cost, how effective the cost is. Well, the cost is not that expensive because you don't need a lot of nanoparticles. You need very small amount. It's very reactive. Mostly it's because of injections as well as efficiency in identifying that locations. So that's why you see there are different ways people do. They add injections, or they could have this permeable reactive barrier. So that's why you don't have to inject anything. You just mix nanoparticles in that permeable wall. And so as the contaminated water moves through that, it's going to be purified. So most of the designs are basically this, because it's very difficult to they realize sooner or later it's very difficult to inject nanoparticles into anywhere without it being loses efficiency. So the transportation is the biggest issues here. So again, this is another reason just to show that if you inject nanoparticles, it will degrade pollutants like this in the subsurface. You can do all that. So this is where they're injecting nanoparticles. So again, I don't know what kind of projects you need it for nanoparticles, but just know that this is one way. Okay, mostly TCE, PC. Anytime you have chlorinated solvent in your subsurface or groundwater, you may consider this as a technology. But in my understanding, um, the delivery is always going to be a difficulty. So the reason delivery is a difficulty is because of aggregations. The aggregation is all about um, um, all about when you have particles, they come together. That's what we call aggregations. Okay, and the size increases, so that means it's going to settle, settle, filtered, and deposited. That means it's no longer available in water to react with other stuffs. So these are the three factors that we have to check. Stability means can it stay as a single nanoparticles. And to enhance that one, a lot of times you add these organics. So the organic comes in between the nanoparticles, so then they are not going to react. They kind of stabilize them. So that prevent aggregations, that prevent also depositions. So that's why a lot of time natural organic matter is added to the system. So the driver of process is how they react with soil. Controlling factor is size. If your size is increases, your reactivity. This is something we already learned. Reactivity decreases. So you wanted to make sure that they are not aggregated. Another factor is their surface charge. As you say, iron zero valent iron doesn't have any charge, but when it become corroded, iron oxide, um, oxide FeOH, all these have net positive charge at certain pH, at least the relevant pH. If it is positively charged, they are going to bind with soil because soil is negatively charged. So you want to also think of what charge it is. You don't want them to be same different charge than soil, because if it is, it's going to stick with the soil as opposed to stay in the solutions. And so the way to address this one is add organic coating or dispersion, like I said here, and change the pH such a way. pH changes is not easy, but if you are injecting solutions into groundwater or the delivery solutions, you can keep the pH such a way that it's stable. So once it's ready, it's fine. But mostly organic coating is the main way to apply that one. And so now the reason how why they works is just want to show is the interaction energy. That's KT over here. I'm not writing equations, but just know that as the distance changes, as the nanoparticles come close to each other, they will experience that energy, and that's the energy that we form here. And that energy depends on different types of the pH and ionic strength. And basically just to show that this is like a barrier. So if your interaction energy is like this, if it is negative, it's attraction. If it is positive, it's repulsion. So the way it is written here is that if it's positive or the bump, the that bump has to be overcome before they can stick with each other. And so that's the reason we have to think of when that this is like a barrier. Okay, think of a barrier energy. What it means that if your nanoparticle is as 50 nanometer distance, they have attractions because there is no barrier. As they come closer to each other, because they have similar charge, they experience this electrostatic barrier because they have same charge, they cannot come closer anymore. And so why it is important? Because if they maintain that, you are not going to have that aggregations. They are going to be stable in the environment. It turns out this barrier depends on ionic strength as well as pH. If it is high ionic strength, which is the case here, aggregation or depositions, if it is high ionic strength, the ions are around. So I'm just going to explain that here. Um, Let me show wherever it is. So if you have ionic strength, high ionic strength, what will happen? It's over here, written here. So if you see over here, 0.1, very high ionic strength. If the interaction energy is always negative, that means always attractive. As the as the as the ionic strength decreases, interaction energy is become a barrier. So that means it's not going to react. So what does that means in the real world situation? It means that if you have lots of salt in your groundwater, it will make the nanoparticles react with each other more. So that means it's going to aggregate, it's going to settle out. So you're not going to have effective treatment. And whereas if you have really clean water, ionic strength means it has less salt, less other form of ions, then it is going to stay stable. So that's important because if your groundwater has a high salinity, yes, nanoparticle is not something you want to use because this is going to be aggregated. It's not going to be reactive. So this is just one implications. And the reason why it case works that way, if you think of why things stop aggregate, you have positive ion. Let's say this is iron, another positive. So they have a repulsion. But if you have, let's say, high salt content, the negative ions it will it will block these things. So it will neutralize that charge to some extent. So that means they are not going to experience that repulsion. When they don't experience that repulsion, they are able to stick with each other and then will form aggregate. So that's why you do not want high salinity. So high salinity is in effect is detrimental to nanoparticles stability. Means they are not single nanoparticles anymore. So that's one thing you have to think of. And the pH is the same thing. If you increase the pH or decrease the pH based on the surface charge, it's going to either become more positive or negative. So if it become neutral or less negative, that means it's towards the neutral, then it's going to start aggregation. So anytime you have to think of what's the effect of pH, then you have to think what pH does. It just makes it more neutral because everything has a surface charge, all nanoparticles. If the surface charge is increasing, that means more repulsion, so that it's going to be stable. If it's decreasing towards zero, that means it's going to be less repulsion, so it will start aggregations. So when you think of pH effect, you have to think of that way. Okay, so if the pH increases, it becomes more negative surface charge, or less positive. Okay, so the positive charge decreases. Okay, so that's the important concept. Your positive charge decreases. That means it begin with positive, that means if your pH increase, it become more neutral. So that means it's going to start aggregating because your charge is decreasing. But it's already negative, and you add more pH, it become more negative. So that means repulsion will increase. So that means it's not going to aggregate. Okay, so there is a two way to think of it. All right, so let's see the quiz to see how well you understand this concept. Increase in ionic strength decreases aggregation of nanoparticles. Is this true or false? Increase the ionic strength means you have more ions. Okay, so I'm going to end the poll and share the results. Um, so as you see over here, increased ionic strength is, let's see, increased ionic strength, if increases, so what happens? You have more ions. If there are more ions, more sealed. Okay, so that because all nanoparticles have same charge, at least the same kind of nanoparticles. So that means the ions will cover them. So that means more shielding here. They're more sealed, they can actually come closer to each other and bind together. Okay, so that's one way to write it. So that means less repulsion. Repulsion is decreasing. That means more aggregations. So decreasing aggregation is a false. Okay. Increase in pH increases aggregation of GBI nanoparticles. That's a can't tell. based on the information provided here. That's option C, let's say. And I would say this is a tricky question, this one. If you have not answered, you can think of based on what we just covered. Okay, I'm going to stop it because this is anyway, I just said it's a tricky question. So share results, you have a mixed solution. So let's see what is happening. Increase in pH. So again, if when you think of aggregation, it's related to surface charge. If the surface charge is becoming more positive, means similar charge, then it's going to repulse. Or if becoming more negative, it's going to repel. If it's becoming towards neutral, that's where the aggregation happens a lot. So what it does, increase in pH, decrease aggregations of zero-valent iron nanoparticles. So zero-valent iron nanoparticles are positively charged. Okay, so if you increase the pH, it's become towards the neutral. So GBI also it depends on pH, where exactly it is. That's a neutral pH. Is net positive charge. So that means if you increase the pH, what you are doing is you are adding more OH. So if you're adding more OH, what happens? You are going to attract that zero valent ion positive charge with the OH. That means that net positive charge is becoming zero, okay, or towards the neutral. So that means your surface charge, positive charge, is approached towards zero or neutral. If it's neutral, there is no repulsion. That means more aggregations, less repulsions. Okay, so that means if you increase the pH, it is going to increase aggregation. So the answer is false. Okay, but if I didn't tell you exactly what initial positive charge, then that could be, you can say also, you cannot tell unless I say what exactly the initial charge was. If I say it has positive charge, then you can answer false. If I say initially it begin with negative charge, obviously the answer is true, because becoming more negative, it's going to start repelling. Okay, so
Excuse me, could you repeat what CVI means again?
zero valent iron.
Okay, thank you.
Zero valent, basically iron particles, iron metals. And zero valence irons, iron oxide, they are going to be positively charged because of corrosion. Okay, UVI corrosions because of that. Iron oxide usually net positive charge. Okay, it's not always true. Its charge is also changed with pH. So at neutral pH, usually net positive charge. Not all type of mineral though, but it's just a perception. All right, so the final thing is there are a couple of things you can change. You can change the coating, you can change the size, you can speed at which inject, the pH, if you have any other materials there so that it can aggregate. So this will all affect aggregations. Then what kind of shape it is? Is this a fiber shape or this is a spherical shape? This will affect depositions. So that's all you do, So these are things you can change the pH, change the ionic strength, compositions, all that you can. So this articles is going to explain if you want to use nanomaterials as a remediations, this is the place to want to look for your projects. And so again, just to show that nanoparticles can be coated with natural environment, organic carbons, organic metal that will decrease their aggregations. So if you have more organic matters, that means nanoparticles have organic matter. Let's say this is organic matter. So what does that mean? That means all that positive charge is not going to be experienced by another nanoparticles. So that means they are no longer going to um, going to experience with each other, or at least they will not. It's another way to say it. They'll. This is not charge based. This is basically they will not react with each other because they don't see each other. It's not about positive charge only. It's also other factors because this organic carbon has their own charge. So they basically dominate it. So once their surface is negative charge because of organic carbons, they everything organic soil are negatively charged, so they are going to repel with each other. So that means they are not going to react with anything; they'll move faster. So if you have more organic matters, your aggregations less transport, so that means your nanoparticle transport will be more. That's your target. So that's just so here reactivity is changed with a different pH just to show that it's aggregation. So that's why as you increase the pH, the reaction is decreasing because they are aggregating. So that's another thing. I'm not going to discuss this one just to show that nanoparticle can be many metal. This is not just iron. There could be many other metals. They could be combination of metals. The advantage of combination of metals is one is reduction, another is oxidations. So we can reaction will be much efficient as opposed to looking for another couples like oxygen. So your reaction can happen on the surface itself. So this is just extra information if you are working on your projects with nanoparticles. This is just to show that any kind of TCE or chlorinated solvent, you can use these nanoparticles to degrade. All right, so that's the summary. Size matters. If you're increasing the size, you're increasing reactions. These are the four different forms that by which nanoparticles can kill or degrade a contaminants by reductions, by giving electrons, by oxidation, creating radicals, or it can create the areas of high surface area so things can bind, or it could be inactivations. Inactivation means you create the radicals that will destroy the pathogens. And as the delivery, if your aggregation size increases, your delivery is less efficient. So any system where the size increases, you can say the transport is going to decrease. Depositions, if you have more deposited, obviously your effective concentration in the suspension will decrease, the efficiency will decrease. And then obviously the nanoparticle itself can transform, and that will make it difficult to um, react. So you got to think of all that aspect. So that's all for the class today. And a project outline, I again just meet with me and I just leave it here. Just in case if you have not made before, you got to think of all that. Again, this is not applied for every type of project, just to give idea, based on one type. Just one thing I want to say that your title should be catchy, like newsworthy, so that you can feel like there is a need, somebody is going to be interested, and rest of them you just change to bunch of questions. Okay, so that's all for the class today, and I will see you next class. I will stick around if you have any question about homework. But most importantly, next class I will discuss about the quiz that is on Thursday, because that way at least I'll give you some reading guide so that you know what are the things I'm looking for. This way you don't feel like surprised when during the quiz like it happened last quiz. But normally everybody does well in this quiz, at least in last 2 3 years. So I think you should be able to do well. Okay, so I'm going to stop sharing and I'm going to stop recording. If you have any question, I'll stick around.